Hello, everybody. So first of all, it has been a great journey to participate in this fellowship program, and I'd like to thank my mentors, my advisor, and my peer fellow students. So the topic of my project is power plant pollution monitoring via bandit algorithms, and I'm Tianyu Wang. I'm a PhD student in the CS department. And this work is partially based on a joint work with Weicheng Ye, Dao Yipeng, and Cynthia Rudin. So as I learned from this program, in particular from my friend Edgar, so in the US, for the pollution monitoring in power plants, we have a pretty nice system called continuous emission monitoring system. But in many less developed countries, people have to periodically, manually spot check those power plants, meaning that the government sends a person to there and takes the number down from there. And the challenge is that it is very costly to always spot check all of the power plants. And very naturally, a question to ask is, which one should we check at each time point? And the solution, a very natural solution, is at each time we only check one of the power plants, and hopefully that one is the most polluting one. And by knowing the most polluting one, we know that overall all the power plants are not polluting too much. So at this point, we abstract this problem into a contextual bandit problem, which is kind of a short-sighted reinforcement learning problem. So in this problem, at each time t, we observe some context information. For example, time, weather, etc., denoted by zt. And based on that information, as well as our past experience, we pick an action. In our case, that could be a power plant, denoted AT. And our goal is to overall minimize the regret, meaning that we spot check more polluting power plants more frequently. And to quantify that, we define the reward, or the expected reward. In our case, it's a pollution. In our case, it is a bad reward. We define the reward on the joint place of context and action from to unit interval. And the regret at each time is measured as the reward, the best reward given the current context minus the reward of your choice. And we sum them up, and that gives you the total regret. So that's the problem of contextual bandit, and that's how we will formulate the manual spot check as a short-sighted reinforcement learning problem. And our algorithm is to, at each time step t, based on the past data we have, the past context, past action, past reward we observe, here y is the reward we observe, we choose an action, we fit a regression tree based on all the past observations, and we choose an action which maximizes the function value of our model plus an uncertainty term. And that uncertainty term is composed of a concentration term, which is the number of past data points in the same leaf as the action you're considering, and the diameter of the leaf that containing the action you're considering. And after we make that choice, we observe the corresponding reward of the choice. And for this algorithm, under some extra assumptions, if the environment doesn't change, meaning that the reward function doesn't change, then the expected reward is asymptotically 0, which means we will always spot check the most polluting power plant in the long run. So now let's test this method on a real data set. So the problem we will verify, on which we will verify our idea, is to track the highest temperature in a building. And then, by the way, the data we will use is from Intel Lab, Berkeley. So formulate this highest temperature tracking problem into our framework. At each time t, we know the following from the past: the wall clock time, which is the context; the monitor selected, which is the action or past action, as analog to the power plant selected, and observed temperatures from the selected monitors y. And on the right is on the right is a table. It's a snapshot of the data table. Further, we fit a model based on the time and ID, which is the context action space, to the temperature, and we select the monitor to maximize our fitted function value plus the uncertainty. As we have discussed before, this uncertainty is a concentration type of uncertainty plus the leaf size of the leaf. And this is the map of the sensors and the map of the building. So each black dot with each numbered black dot is a sensor, and this is a chicken. This is a kitchen. This is a storage. This is a general map of the building. And this is our result. So the Duke-Blot dots represent the error induced by our proposed method, and the red dot is the error for a random method. And here the error is measured with respect to the true highest temperature at that time. So as we can see from this plot, using only 1 out of 32 sensors, we can, using our method, we can get a fairly good estimation of the highest temperature as opposed to randomly selected a sensor, or in the power plant setting, randomly select a power plant and send person to there. And that's all of my presentation. Thank you.
Thank you.